In the previous class, we were essentially looking at how memory is managed. And to quickly summarize this, what we have is the virtual memory. It requires, to support virtual memory in a system, it requires not just the operating system to support, but also the processor, right? Now, what we have is a CPU core, right? And every time the CPU wants to load or store some data or to load an instruction, it essentially puts out a virtual address. Okay. Now the memory management unit, or the MMU, uses a sequence of page tables, right? Typically a hierarchy of page tables. Right, to convert the virtual address to a corresponding physical address. Right, and this physical address is then looked up into the DRAM. Right, so any load or store or any instruction that is going to be fetched into the CPU core would essentially go through this translation, unless there is a caching of this virtual to physical conversion in a small cache present in the CPU called the TLB, or the translation look aside buffer. So, so here is where there is an interplay between the hardware and the operating system, right? So the memory management unit is essentially part of the hardware, right? And it takes a virtual address, converts it to a physical address. The setting up of these page tables and the page directory and so on, and each page table entry, which is each entry into these page tables, is essentially done by the operating system, right? So unless the OS sets up these page tables and the page directory and enables this translation from virtual to physical address, only then will this entire scheme work, right? So now there is an issue. So what happens during booting, right? So you turn on the CPU, and as we have discussed before, the CPU is turned on and with a reset pulse. And at that particular instant, you do not have anything which is being executed, right? So the OS has not been set up and so on. So as a result, we do not have these page tables and page directories present in the RAM, right? So what happens at that time, right? So soon after booting, this concept of virtual memory is not enabled, right? So at booting, virtual memory is not enabled. It requires the OS to set up these at least one level of page tables, page directories, and then enable this memory management unit, and only then will this mapping from virtual to physical address with the help of these page tables be enabled. Okay, so so prior to this, right, prior to the MMU being enabled, the physical address is going to be equal to the virtual address. So in other words, the CPU puts out a particular address on the bus, and this address is essentially just the physical address, right? So if you recollect, and also we will see a few classes later, sometime later as well. So when the CPU starts to execute, it starts in XV6. It starts with this file called entry.s, and then entry.s calls a function in start.c, which then invokes this function called main, right? So the execution from entry.s and start.c is essentially done with the MMU disabled, right? So therefore, the virtual address is equal to the physical address, and the MMU is not playing any part of it, and the DRAM is directly accessed. Now, in the main function, before turning on the memory management unit, the kernel would have to set up these this hierarchy of page tables, right? So we are going to see that process now, about how the kernel would set up what is called as the kernel virtual address space, and then turn on the memory management unit, and then thereby enable the conversion from virtual to physical address, right? Now, in order to create this concept of kernel virtual address space, the OS needs to know about the memory map of the system, right? And so it creates this virtual address space considering the memory map of the system, right? Therefore, the kernel's virtual address space for one system would be different from that of another system, because like we mentioned in the earlier videos, the memory map of one system is different from compared to another, and therefore the way the kernel's virtual address space is created is also going to be different, right? So we'll first look at what is the memory map for QEMU, right? Why do we need this? Why do we need this? Because QEMU is essentially our emulator, right? So it emulates the system, and therefore it has its own unique memory map. Now we need to understand this particular memory map and then create our kernel virtual address space according to this memory map. Okay, so so the memory map for QEMU is essentially how these physical addresses are organized, right? So we see some layout over here. We have a lot of unused spaces in the physical address map for QEMU. There is some portion where there is RAM. There is the UART, which is the serial communication, and so on, right? There's a little bit of information which is not present here, but we can essentially look at this particular file called memlayout.h. That is here, right? So I go back to my x86 source code, look at mem layout.h, right? So what you see over here is essentially the memory layout for the QEMU virtual machine, right? If you have the QEMU source code, you can look into this particular file, hardware/disk-free word C, which is essentially where this particular memory map for QEMU is present. The summary of this entire memory map is present over here, right? So at the location 0x1000 is where you have the boot ROM, which is provided by QEMU. This is an internal address by QEMU, which essentially simply jumps to this location 80 million. And as we've seen before, at 80 million is where your kernel is present, where your physical memory, physical RAM is essentially present, right? So starting from 80 million going upwards is where you would have your RAM, right? And as we've seen before, the x86 source code and the code and data would essentially start from 80 million. Okay. Now, besides the boot ROM, that is this, and the RAM, there are a few peripherals which are supported, right? So one important thing is the UART0, which we will be using for communication. This is at 10 million. And like we have discussed earlier, this UART0 is used to transmit or receive data to and from from and to the QEMU emulator, right? at the location 0x1000 100 you have the virt IO disk. So this essentially is a virtual IO disk. So it kind of mimics the hard disk, and essentially is present at some location, right? Now, besides this, you have one more thing known as the clint and the plic, right? So clint and plic are essentially related to the interrupt controllers. The interrupts, are essentially the interrupts which you will be actually seeing later on. Okay. Now, if I go down into this file, I see there are various hash defines that define these various peripherals. For example, I have a hash define UART 0, which essentially states that my UART starts at the location 10 followed by 6 zeros, right? So similarly, I have this virt IO 0 which starts at the address 0x100 right? And clint, plic, almost all the devices that we want over here is essentially present. So recollect also that the kernel starts at the location 80 million, right? And it's defined by this point called kern base, right? And the physical stop, right? The physical stop is the maximum location of the RAM. So 80 million over here is the lowest, the starting location where the RAM is present. So 80 million plus some amount of memory is where the RAM ends. So this is called as the phi stop or the physical stop, which is essentially kept at 128 megabytes. So we are assuming here in our system that we have 1 megabytes of RAM present, and we are going to use this RAM to store the kernel source code data, but to also use it for other things like running user programs, creating page tables, and so on. Okay, there's a lot of other things that are also present in this particular file, which we'll be seeing later on. For example, when we study interrupts, we'll be looking at what this UART 0 IRQ means and virt IO 0 IRQ means and so on. But for now, and similarly the aspect of trampoline and K-stack and so on, we'll be seeing as we progress. But for now, we'll just look at this concept of the memory map, right? So here is the summary. We have not shown the addresses in this particular picture, but we have just shown the physical address where these various devices, peripherals, RAM, and so on are present, right? And what we need to essentially do is create a virtual address space for the kernel, right, which maps from this virtual space into the physical space, right? So here is what we actually need. So before we enable the memory management unit, we would need to create this virtual address space which maps to the corresponding physical address space, right? So what you would see is that there are some things which are mapped directly, that is, for example, the kernel base at 80 million directly maps to the start of the physical memory, right? So at this location, as we've seen, we have the entry.s and start.c and so on, and the various other code, right, in what we call as the kernel text, right? After the entire kernel text or kernel code, we have the kernel data. So this is again directly mapped into the physical memory. When I say directly map, it means that at a location 80 million in the virtual address space maps to 80 million in the physical address space, right? So there is a direct one-to-one map that is present, right? And so the kernel data here essentially is read-write data. What it means is that these are essentially the global data that is present and used in the kernel, and above this data is the free memory, right? Recollect in our previous video we have showed how this free memory is configured into chunks of 4 kilobytes and essentially configured as a linked list, and with the help of two functions calloc and kfree, the the kernel can pick a particular page frame to be used, and once the page frame is completed its use, it can be put back into the linked list using the function kfree. So all this kmalloc, kfree and so on work in this free memory region. Okay, so so we see that besides the kernel data, kernel code, kernel data and so on, every device, right, the UART, the PLIC, the CLINT and the VertIO device are very similarly directly mapped to the corresponding physical addresses, right. So for instance, at at 2 million is where the CLINT, that's the local interrupt controller, is getting mapped, and it's mapped directly to the physical address, which is also present at that same location at same address, which is 2 million, right. Similarly, for the other devices also, like the UART0 is mapped directly and so on, right. So why do you need to map these devices, right? Why do you need to map each of these devices present to the corresponding physical address? The reason is that once the memory management unit is turned on, every address emitted out of the CPU is considered as a virtual address and needs to be translated to a corresponding physical address, right? And therefore, if the CPU wants to say transmit or receive data through the UART, it needs to send out some address in this range of say 10 million, and this 10 million address needs to be converted to a physical address, because the 10 million which is sent out is a virtual address and needs to be converted to a corresponding physical address to access the read and write register, the config register or the status register present in the UART, right. But yeah, but we also see that there are some mappings which are not directly mapped, right. So for example, we have certain things like the trampoline, you have kstack, the kernel stacks and so on, which are not directly mapped. So what does this essentially mean, right? So this essentially means that at the address present over here, right, kstack 0 in the virtual address space, there is some page translation which converts this particular virtual address to some physical address in this range of close to 80 million, right. Okay. So similarly, for the other things like the trampoline, the guard pages and so on are essentially translated from this higher address in the virtual address space to a physical address which is in the region of 80 million or so. Okay. Now, you would notice something very interesting, right. What we have said is two things. First, we said that there is a direct map that exists. So, kernel code and data, there are page table entries or like a hierarchy of page table entries which converts each address, say from this location to a particular address over here, right. Similarly, an address over here in say the kstack 0 is also converted to the physical address, right. So what it means is that there are for this physical address present over here, right, there are two ways to access this particular address, either through this virtual address say v1 or by a virtual address say v2, right. So how is this possible? Essentially because we are using this hierarchy of page table the page directory and page table entries to convert this virtual address to the corresponding physical address. So I could put the virtual address v1, it goes through the translation of page directory and page tables and so on, and then I will get the physical address say p1, right. Similarly, if I put say v2 to the same hierarchy, I have mapped these page table entries in a way that even for v2 it gives me the same output, same physical address output P1, right. So what does this mean is that I can access the same data from two addresses within my virtual address space. Okay. So yeah, so this is what is mentioned in this slide. Some regions like the stack can be accessed by two virtual addresses. One is a direct address because which is essentially over here, like you have the data which is directly accessed, and the other one is the indirect access, which is essentially from these regions by where you have page table entries in the page tables, which map this high value of virtual address to the corresponding physical address.